All right, everyone, welcome back to the Water, Wetlands, and Watersheds seminar. It is Wednesday, September 15th. Today we are lucky enough to have Dr. Myoseon Jang with us today. Dr. Jang is an associate professor at UF, and she has 28 years of experience in studying atmospheric aerosols, both modeling, field experiments, chamber simulations. Her efforts are used to benefit research on how climate affects aerosol optical properties, as well as the health of humans, so pulmonary health, both through in vitro exposure methods and the discovery of specific toxicity methods or mechanisms. She's looked at now red tide, cyanobacterial blooms, hydrocarbons, mineral dust, even sandstorms, biomass burning for energy, and all sorts of other aerosols in the environment and their effect on humans and ecosystems. Dr. Jang has a heavy emphasis on getting her work out to the international community and has held a number of international workshops, scholarships, and research projects, and also educational programs. So Myoseon, Dr. Jang, thank you so much for being with us today. Please, the floor is yours.
Great. Thanks so much, David, for introducing me to the audience. Hello, still good morning, right? It is nice to meet you, everyone. And I'm going to talk about today atmospheric process of aerosolized algal toxin generated from red and green water. I'm not talking about Christmas tree ornament. I'm talking about water, red water and green water. Okay. Okay, this is my research, and I start from what I'm doing. And then if you have a chance, if you come to UF campus, and then if you have a chance to look at the top of the black hole, and then you can see the strange large reactor. That this is the atmospheric photochemical reactor to simulate all kind of a toxin or all kind of combustion aerosol, all kind of any aerosol gas simulation. Then I study, as David introduced, I study all the diverse gas and particle. And then nowadays, and then my research expanded to ocean, and then because of problem of red, green algae from the freshwater and ocean. And also my research even extended to very dry region, no water region. Then I study mineral dust from Sahara dust and from the Gobi Desert. But actually this one is by each other, but it is, and actually this one is connected. You never imagine even dust is far from the ocean, dust is connected to the algae issue. But I'm not going to talk about too much about this kind of thing. That we are in the one atmosphere. So this is an overview of today's presentation. I will briefly give a background and motivation, and followed by the experiment which I use. Then I will talk about result, some observation from chamber in the field. Then I will conclude by giving challenging issue for the future study. Okay, then this is recently I take the photo. This is last month, August 2nd and August 21. And then you can see the left side, that is my foot. Then you can see the fish size, it is humongous, right? Even large fish die, means like toxic level is high because the large body is more endurable for the situation. Even large body died means like a toxic level is very high. Then I went to beach to measure the toxic algal level, and then I can introduce soon. And as you know that the water people already, you guys exposed to all kind of impact, human impact on water, and then why the green algae, red algae is become larger, and then you already heard about this. And then human impact, agricultural activity, and then nutrient is washed out by rain, and then also people use land use, and then wetland is getting smaller, and then makes more problem. And water consumption, wastewater is washed out to the ocean and lake, and then frequency of storm is high, and also climate change make impact. And then there are two types of algae, and then ocean salty water, and then green blue algae in fresh water. this impact, this human impact influence both water. So we cannot escape salty water, fresh water. Oh, so no way to go. The type of the toxic algae is in the salty water is Karenia brevis, and then the freshwater side is cyanobacteria. Then toxin from this algae in the salty water side, notorious one is brevetoxin, and the green algae side is microcystin. And then these two toxins can cause different effect. The ocean side is it is known that cause neurotoxin, and then fresh algae cause hepatotoxin. It is not just limited to this. They can have a little bit of a component if they have a pulmonary the toxicity level out there. Okay, so this is just because I say toxin, then just show the structure of brevetoxin and the microcystin in cyanobacteria. And then later time, I point out something, but brevetoxin and neurotoxin, this is a long, looks like a chain of the ether compound. And then you see the red circle, and then this pointing is this red, the alkene double bond is usually highly reactive. For example, microcystin at the bottom side, and then the other unit, there is you can see the two double bond, right? You can see the two conjugated double bond. Other unit is very active, reactive to even the human body toxic level. And then also this two double bond is very highly reactive with the atmospheric oxidant. So it means there is a two meaning, like a double bond is toxic in human body, and also this double bond is highly reactive, and then they can be changed in atmosphere. Okay, and then lots of people talking about human impact through the water. And then another fundamental question is how about the air pollution? Air pollution can increase algal bloom? My answer is yes. And then water side, people talking about agriculture, what the nutrient wash out, but air side, NOx. And then if you have automobile combustion, high temperature burning, all the time produce NOx, NO and NO2. And then this NOx can become nitric acid in atmosphere. This nitric acid is can be deposited to the soil by wet deposition and dry deposition. They can increase nitrate concentration. So even the air pollution can increase algal bloom. And then also mineral dust, usually from the Sahara dust, Sahara or Mongolia, and even they travel to West Coast, East Coast, both. The Florida, every summer we have the mineral dust from the Sahara desert. And then this one can also increase algal bloom. Why? Because there's iron oxide, and then this is a catalyzer to the algae and some other plankton. But mineral dust has a two story. Like majority of ocean people, they welcome. Coastal people near the seashore, we don't want it. But ocean people, they want. Why? Because without mineral dust and the plankton is a shortage. And then they worry about fishery. The food chain can have a problem. And then also another thing is climate change is directly connected to air pollution, definitely CO2 and all kind of the air pollutant which we emit. And then they change temperature, and then warm water is sometimes a favor for algal bloom. And then upon this, algae is a sunlight receiver. Then if algae bloom appear, and then also ocean temperature become higher because of algae. It's a kind of synergetic effect. So also another thing is CO2, and then CO2 is a food for all kind of phytoplankton, any the green stuff, right? So air pollution also connected to algae bloom. Here is a diagram, and then water people all the time talking about water side, but the ocean, if you go to ocean, you see the wave. Tons of wave, and then this wave can produce sea salt aerosol. Then this sea salt aerosol amount is not small. Then this sea salt aerosol is transferred by wind to the coastal community. And then cyanobacteria, same thing, the freshwater lake, then they have the water, the turbulence of water, and then produces cyanobacteria aerosol. So this aerosol is dispersed through the wind and also deposition by particle size. Then upon this, there is also atmospheric process because this aerosol is in contact with atmospheric oxidant. And then this all of thing is unknown so far. Okay, and then the people talking about the respiratory, the algae impact on respiratory. Then you need to pay attention because usually sea salt particle size is much larger than combustion aerosol. Some of the sea salt is particle size is even larger than 5 micrometer up to 10 micro, 20 micro. Then usually that large particle is deposited nose area. It cannot go to the tip lung. Problem is if your particle go to the nose area, then which part is damaged? Usually brain. And then some people worry about algal toxin can damage the brain because large particle, the one concern is the particle size is larger. The large mass is start on nose and then this one is directly connected to your brain. Then one possibility is neurotoxicity, brain damage, and then some people worry about Alzheimer, dementia. Then another part, and the particle is getting smaller, then they can transport longer distance. And that means the infection is larger, area-wise larger, but the amount is less, but they can go to the deep lung. And then that can make the pulmonary and the cardiological effect, and then it damages for different mechanism. Even this kind of mechanism is unknown, like what size of particle algal aerosol go to the which area, how much, and then this is totally unknown. I just give the attention to audience. And first time, like I show that everything is connected, and then similar picture, and then I try to show that why it is connected. And then we emit all kind of pollutants, and then all of pollutant can participate photochemical reaction. I don't want to explain the complicated photochemical reaction today, but this reaction can introduce OH and ozone and oxidant. This one is go to the ocean area. And then this one is combined with the sea spray aerosol or lake spray aerosol, and then mix and then change the lifetime. Okay, and then also we are under the sun. And the sun makes another complication. So our motivation, what is the lifetime of aerosolized algal toxin, algae aerosol itself, and toxin? Okay, so experimental by using UF-APHOR Chamber. So few slides, I will show that how I approach and how I study the atmospheric process of algal aerosol. Okay. There's a large outdoor chamber. I just give several examples because some people doesn't understand what is a large outdoor chamber. Whole worldwide, there are large outdoor chamber. And the UF-APHOR Chamber is one of them. And then this is like a large classroom size. And then you can see the student and compared to reactor, and then you see that reactor is huge, right? And then my chamber is gold chamber, and no, it's not gold chamber. I took the picture and the sun set, and then it's by diffraction, and then it looks like a gold color. Then sometimes it looks like a silver color. Okay, so this chamber is bisected, and then two chamber. It means like I can conduct the two chamber experiment under the same meteorological condition. Because the experiment all the time we need the comparison as a reference condition, and then if you change the parameter, right? So it's very convenient. So chamber, then we have a chamber, then we have aerosol from source, like for example, red tie algae we sampled last year by helping from the MOTRAB, and then sample was collected October during the bloom season, and then we bring the seawater to the chamber, and then we nebulize. So we make aerosol to the chamber. And green algae's case also same thing. We sampled the cell line was extracted heavy bloom season and then cultured by Dr. Dale Loppinghouse, and then we have that the green algae, the cell line, the product, the algae solution, it looks like a soup, and then we introduce the aerosol to the chamber. So each chamber, one side have green algae. No, it's a different time. Like we study both red algae and green algae. And then red algae's case, and the brevetoxin is inside the red tie algae. The green algae is the MC-LR microcystin is with the green algae component. Okay, then measurement and then correction. This is another challenge. So we try to avoid the use of filter. The filter aerosol correction by using filter is a popular technique because of simplicity, but we try to avoid. Because the reason is algae has lots of protein, lipid, and even sugar structure. And then the toxin is agglomerate with those organic components. And then if we try to extract from the filter, and then filter can bother extraction. So we try to avoid the filter, and then we use a new technology that we call particle into liquid sampler. And then you see the red ball. Let me, can I have a pen? Oh, okay, that. Okay, so red ball, you can go to the red ball is impacted at the fast flow. And then this is the impacted ball is by the high humidity, and the ball size getting larger. Then during that process, and then automatically the aerosol is extracted without filter, and then we correct the aerosol. And then if we correct about 10 to 20 minutes, and then this is enough to detect toxic level in our aerosol. So short time, if high efficiency sampling correction allow us to study decay of algal toxin over the course of experiment. If sampling takes a long time, 1 hour, 2 hours, and then that time scale is too large to study photochemical reaction of algae. Then I can show the later time result. So we measure gas, particle, and the toxic level, brevetoxin, microcystin by use ELISA and LC mass spectrometry. The LC mass allowed to analyze conjugate, the different types of brevetoxin inside, and microcystin same thing. So we measure ozone, chamber dilution, and then particle size distribution. And then I don't want to go detail, but for example, sea salt case, we measure salt content and then composition. And also even we measure the chlorophyll degradation in the algal aerosol. This is very important information. So we measure all kinds of things, and we use to understand the algae transformation in atmosphere. Okay, so we have a chamber observation, and then I will show some result. Okay. So first thing, then let me go to the microcystin, and in the cyanobacteria, this is from fresh water. Yeah, I will show something result. I will show first the green algae. So cyanobacteria, then MC-LR, this is a structure, and then fundamentally microcystin is comprised of 7 aminoic acid. So it looks like a cloud by 7 aminoic acid. And then especially you see the ADA unit, these people, it is known that ADA unit is the key component to produce toxicity of microcystin. And then you see that there is a conjugated double bond, and the CC unit, and then this one is highly reactive to human body. Then another thing is that this CC, the carbon bond alkane double bond is highly reactive to atmosphere, the atmospheric oxidant. So you can see that. And this is a result. First thing, we start to expose cyanobacteria algae to ozone nighttime without sunlight. So only chamber has ozone. Why? ozone is formed in the daytime, and then they can survive even nighttime. Like 20 to 30 ppb of ozone is very common even nighttime. Like ozone maybe disappear, maybe 2 a.m., 3 a.m. slowly they start to disappear, but up to like mid 12 o'clock midnight, you can see the ozone. So this is without sunlight, and then you can see that green. This is a ELISA, the other base ELISA, and the measurement, and then you can see that very fast decay. Within 2 hours, the ozone concentration is 60 ppb, and then usually nighttime 30. And this daytime even higher than 60 ppb is common. So this is ambient level. It's not just to like over injection of ozone, not that situation. And then you see that then the microcystin decay is very fast. And we calculate based on pseudo post-odor approach, and then the concept we calculate the rate constant of ozone, and then with that condition 60 ppb, and then lifetime is only 54 minutes. It's shorter than 1 hour. So it means very fast. So without understanding of dynamics of atmospheric chemistry in algae aerosol, and then talking about impact or talking about some other effect is limited, then we have to understand this. So another thing is this time we tried exposed to under the sunlight. The algae was suntan, yeah, go to the chamber, the sizzling sunlight, the sun can produce a lot of things. And then decay of toxin under the sunlight is much complicated. Why? I just provide the reason. Reaction with the ozone in the daytime, usually ozone concentration is higher than nighttime. And then also OH radical is involved. There's some of a chemical like Pono and H2O2, this one is a partition to particle phase, and then they can be photolyzed and then produce OH radical. Another complicate, there's a chromophore, and then chlorophyll, humic acid, they receive sunlight, and then they can activate it, and then they can produce a singlet oxygen. This singlet oxygen can react with algal toxin or algae components. They produce radical, and then some other complicated radical species. So by this, and the sunlight is still on the way, we try to make mechanism and kinetics. That's still on the way. We don't have a conclusion yet. What we know is the photochemical under the sunlight, algal toxin and algal transformation will be much faster. And then experiment, we demonstrate. You see that, and then early morning, for example, this data is most of them is collected early spring to the April. Yeah, I didn't write down date. The sun is not high. And then even under the 8 o'clock, sun is very low, and then immediately sunlight come, and then microcystin LR is almost touch down the bottom sometimes. It depends on sunlight intensity. Then ozone cannot explain, even ozone form. And then ozone, so you can see that line, and then dark black line is based on ozone, and then because we have a nighttime ozone rate constant, right? So ozone cannot explain. So it means all kind of this component is involved, and then accelerate the degradation of the toxin. So you can see that, so much faster. Okay, and then how about red tie? And then we have to go to the I will change my gear to the red tie right now. Red tie has what toxin? Brevetoxin, right? Brevetoxin is in red algae. And then one of the difficult one and the sea salt studies, we collect bulk seawater because that water is not from the surface, very thin layer of micelle. And then bulk seawater organic fraction is less than 1%. But sea spray aerosol organic component is 30 to 60%. Why? Because lots of the algae component, those micelle is floating on the water. And then sea spray aerosol is produced top. And then if you measure the sea spray aerosol, organic content is not 1%. It can be 30 to 60%. And then brevetoxin is what is a brevetoxin? Definitely brevetoxin like organic layer. So it means the brevetoxin concentration is where's the brevetoxin? Most of them surface of water. Oh, that is a really unhappy story. Then brevetoxin, so I suppose this one is not published yet. Brevetoxin concentration will be much higher in the sea salt aerosol. That is my assumption. Yep. So right now we see that this brevetoxin was then also the dynamically decay something, and then the chamber study is with bulk seawater, the low concentration of brevetoxin. But the field study we have to demonstrate, or we have to have a special technique to correct only surface water. That is not easy. So this is a brevetoxin concentration, and Caden draw well, and then I just use Caden's material. And then you see that brevetoxin also has a double bond, many places, and then also brevetoxin has a alkyl, the ether linkage, the alkoxide, and then this alkoxide also oxalate reaction, and the brevetoxin also has a high chance to react with atmospheric oxidant. It's not more than body. So we see that ozone, same thing, you will see the similar tendency. Then brevetoxin, the exposed to ozone, decay distantly, right? And then the rate constant is slightly less than microcystin, but similar level. You see the level, I just try to compare. Yeah. And with the 60 ppb of ozone, and the lifetime is a little bit more than 1 hour. Previous one is a little bit less than 1 hour, right? So still, this is quite fast, yeah. And then daytime, same thing, same reason with the green algae, the microcystin, and the decay is much faster. So you can see that. Okay, and then how about the algae itself? Because I'm talking about the toxin in green algae and toxin in red tie algae. How about algae itself? Because algae is there are lots of chlorophyll, for example, lots of lipids, other proteins. And then what I did is, this is the aerosol spectrum, and then I measure chlorophyll concentration, the spectrum in algae. And then you can see that the first one, then green color, and then exposed to 6:30. There is no any light. Then 30 is totally dark. And then 10:30, few hours later, exposed to sunlight, and then decoloring. There is no chlorophyll anymore. Chlorophyll is also dynamically changing. It means algae whole body is dynamically changing. Then afternoon, exposing to several hours of sunlight, there's no color at all, no more color. And also, how about the sea salt? The sea salt also, initially sea salt Na and Cl ratio is about 1:1. I just put the 1, but actually Cl is slightly higher. But you can see that as the time goes, the Cl chloride is depleted because algae is dynamically oxidized and then produce carboxylic acid. Oxidized means usually oxidation level high compound produced. Then usually that one is carboxylic acid. Then that carboxylic acid is combined with NaCl, and then carboxylic acid become Na combined with Na. Then produce HCl, and then HCl is very volatile. So ejected. And then you see that this is real experimental data, and then Cl is start to deplete very rapidly. It means the sea salt's property is changing. And then if sea salt property change, and then this one is also impact on climate change and sunlight reflectivity. So we don't know how much important this one, but I just try to show that algae aerosol is dynamically changing. Toxin change, the algae body itself will change. I try to show that. Then how atmospheric chemistry is powerful. Okay, then I make this morning I made 2 scenarios. And then because I talk about only chemistry, but there is also dilution because wind blowing aerosol concentration is diluted. And then compared to the dilution, and then what is a chemical reaction is powerful compared to the dilution. And then this one doesn't mean like I just said, BTx is 1%. Then by traveling, just I said, it doesn't mean leftover 1% is safer or not safer. This is just a mathematical calculation. Nighttime, under the low ozone, 20 to 30 ppb, and then the concentration of BTx is 1% leftover by traveling. Then how long do I have to travel? That is about 1 kilometer. Then by dilution, because air is diluting. So this calculation can be long, but this is my calculation. Then the 1 kilometer travel, and then already BTx dilute by the air dilution. Then at that time, nighttime, about 5% is contributed by atmospheric process. And then this is my just calculation to show that. Then daytime's case, same condition, the ozone is higher. Daytime even higher than 50, 60 ppb of ozone. And also daytime, there's a other chemical reaction, even one order, like 10 times a fast reaction is possible. But another thing is dilution. Because aerosol is the vertical movement, and then dispersion is faster in daytime. And then 1 kilometer become 0.2 kilometer, but the photochemical reaction and some other things contribute. This is my calculation. It can be more, about 10 to 15% within even 0.2 kilometer, then impacted by atmospheric process. If you go further, it means the contribution of a photochemical reaction is getting larger. Just this one is give a practical sense. If you're walking on the ocean, and then how you can be impacted, and then I try to give you something sense. Okay, then the people showing the several slides of field study, I will try to summarize the chamber observation, and then both the brevetoxin and the microcystin, both toxin can decay by interaction with the ozone. Both toxin also interact with the sunlight, and then there are much more complicated, and then the decay rate is much faster under the sunlight that we observe. And there is a reason I repeat, and the ozone concentration is high in daytime. There is a OH radical source. There is a photolysis of some other chemical species, and then there is a chromophore, which can be excited under the sunlight, and then they can contribute. And also, in addition, composition of aerosolized algal aerosol changing, decoloring, diffusion of the chlorine ion, and then hydroscopicity of aerosol change, and there is a many phenomena. And also aerosolized BTx concentration, I assume it will be much higher. Then also decay of aerosolized algal and then toxin is much faster than in the water. This is specific, unique for atmosphere. Water cannot be that much fast. Then because this one is atmospheric oxidant, and then the lifetime is much shorter. Also, decay does not mean less aerosol toxicity. This one is just for the toxic chemical species, how they decay. But after decay, do they gonna become less toxic? That one, I don't have an answer yet. Okay, and then I will give you several slides about the field study. And then field study, I cannot bring all of equipment, important several instruments I carry to the field, and then August and then last week. And we measure ELISA in aerosol, and then aerosol mass concentration, and then ozone level, and the fundamental, the wind and something sunlight is to be measured. Okay, so here's a portal, and then me and Jason, Karen, Jiwon, and then we go together. And then it's not easy because we have to carry instrument. Then what we see, the interesting is organic matter in sea salt aerosol was much higher. This is a measurement. About 54% is organic in sea spray aerosol. bulk, I told you that is less than 1%. And another thing, BTx concentration is 2 orders higher than bulk phase. This one we didn't publish yet. Then this is a shocking thing because BTx concentration is much higher than bulk phase water. If we nebulize the aerosol to the atmosphere using the bulk, then it cannot be that much high. Why? Because BTx love organic. BTx is organic. And also we see that at that time, that the BTx concentration level is much higher than the pulmonary symptom, like the concentration which can be produced pulmonary symptom, 4 nanogram. This one doesn't mean the toxicity based. This one is like just say, people already start coping. So it means the toxicity even before coping level, right? So no one knows right now. There is no standard and there is no any information, totally unknown. So this is our observation. And next slide is just I try to summarize, and then the challenging issue for algal study. And then first question people will have, how much residential area affected by adverse algal aerosol? This one, everyone is curious. And then to do this one, then the photochemical reaction mechanism of the degradation of algae is mandatory study. Otherwise, the dispersion model cannot explain everything. And even dispersion model, there are many unknown parameters. And the advanced technology, and then to know the algae aerosol dispersion, we need in situ detection of algal aerosol in the 3D to develop the 3D model. It has to be very fast, has to be in situ. And also another thing is we need a better immunoassay. If somebody use immunoassay, then you understand what I mean. The immunoassay is the accuracy is not very high because it's based on calorimetry. They can be up, down, and then we need low level, which can detect low level the brevetoxin or toxic level with the accuracy. That this is another part. The health effect and really what is the toxicity of algal aerosol? The toxic level is very little compared to whole algae body. And then algae body can make a toxicity or toxin can make a toxicity. We don't know why people coping because of brevetoxin or because of algae aerosol itself. Then we don't know. And then also mechanism. Then if we have the coping and the toxic level, what is the mechanism? This is oxidative stress. We don't know. Another one, the beginning of I say, then depend on particle size, and then deposition, it can be nose. That one is a neurotoxin. If they won't go to the tip lung, that one is the impact through the cardiovascular system. And then if particle size is large, and then the depend on region, and then it can be the target should be the pulmonary or target should be the brain, some other damage, and the mechanism is very different. So this is the challenging issue, and then we are now studying all kind of things, the kinetics, and so it's challenging, but I really enjoy this research. Then too many unknown means provide lots of challenging thought and issue. Okay, that's it. And then this research is supported by FWC and NSF. And then you can see that who was involved for the research. Yeah.
Thank you, Dr. Jang. Very much appreciate. Round of applause for Dr. Jang, either real life or in your emojis here, at least. So what a world that we know so little about. It's really amazing to hear you summarize everything from the mechanism of transport to degradation to human toxicity. So let's open it up to questions from the room, and I'll check on the YouTube and see if we have any questions for Dr. Jang. I'll prime the pump. I'll get started because I have a couple of them. Let me try to restate what you found from the sort of the experiments where you simulated like a nighttime and a daytime source, like a line source, and then coming into the shore. So at night, the idea is that within a kilometer, you're 1% of the toxin concentration is present within 1 kilometer, but that 95% or so of the dilution is really dilution rather than reaction.
Yeah, this one is the 1% means by the dispersion, the concentration remained concentration is 1%. 1%. What is the contribution? 95% is dispersion, and the 5% is the chemical reaction.
Right, and then during the day, this the length over which that decline occurs is smaller, so it's happening kind of faster during the day, and the proportion of explanation is larger for the reaction because you have.
Yeah, so this time I didn't combine the how much is dispersion, how much is 5%, because this one is really the integrated modeling. But then what I say is within the 0.2 kilometer, and then 10 to 15% of the BTx can be decayed by photochemical reaction in the absence of dispersion. And then dispersion 0.2 kilometer, they can have 1% remain. So we have to combine two together. Yeah.
Right. So basically the idea that the closer you are to the source, the more important the reaction is in causing the decline.
Sunlight. Yeah.
But also because
the length is shorter, but photochemical reaction is increase more than 1 order. So it's very active. And then contribution is higher in daytime.
So with that kind of combining dispersion modeling and the reaction modeling, and what can you say about like the concentration in the bulk water, and can you then like go from a prediction of the bulk water to the concentration in the organic in the sea spray to the beach itself? So you can combine this like partitioning from the bulk water to the droplets, and then this other model of dispersion and reaction, and make a good prediction about where the beach. So. Can you? Yeah. So how do you associate the concentration in the bulk water to the load in the air, to like the?
They will need another module modeling for the involvement of ocean. The engineer. The first thing is we need to predict flux of sea salt from the ocean, the concentration of sea salt. Then we need also fraction of organic. The organic in the sea spray aerosol. We cannot use a bulk phase. We have to use the surface of the ocean layer, and then that one can produce organic fraction and the seawater fraction. And then based on that, and then if we know the fraction of OM, then we have to see the linear relationship between BTx and OM. And then we know the BTx concentration and OM. And then based on the source, and then we can predict the impacted area of in the coastal area. So we need one more model.
So you need like wind and waves to turn in.
Yeah, right.
You need to get to see aerosol. Yeah. Okay. Mark, you have a question?
Yeah, and it's probably just point of clarification. Is it just the toxin that's aerosolizing, or is it actually the algal cell as well? And if it's both, what is
algal itself, not the toxin. The toxin, the algal aerosol itself contain toxin. So sea spray aerosol we nebulize, and then the freshwater aerosol we nebulize. So it means inside already have a toxin.
So the cell itself is distributing in the air, and so
the cell itself is distributed to the ambient air.
Okay, so any degradation of the toxin is actually having to go through the cell.
Not just a toxin alone with the algae component. It's realistic.
Okay, interesting. Okay.
Because sometimes we hear that the action in the water column can cause cell to break, to cell lyse, and then the toxin is released, at least for red tide. I've heard some about that. So is there, are you able to, I don't know, like distinguish?
Partition, yeah.
You have like the whole cell, like a particle. And I mean, it's all connected, it's all connected to the aerosol. So I guess it's almost all like traveling like a particle like thing, right? it's a whole structure of water and organic material. Some of the materials cell. Some can it transport as just the solubilized toxin in water?
So what I think is, if, let's say even the cell is ruptured in the water, and then most of case, there are lots of pieces of lipids, protein, and cell component. Those components tend to go to the surface of water. Even the continuous dead body, and then they won't go to the surface of water. And then brevetoxin is organic compound. If you think about solubility to the micelle at the top, or the solubility to the sea salt, then brevetoxin, for example, they love to be with the organic layer. So it means why brevetoxin concentration is much higher than bulk phase, the aerosol. We nebulize the bulk the aerosol nebulize, and then we measure the field, and the organic content is high, brevetoxin is high. Because of brevetoxin, they follow the organic layer. Because the solubate comfortable, thermodynamically, they soluble in organic layer. So brevetoxin enrichment on the surface of ocean, it means aerosol content, high concentration of brevetoxin. I mentioned about that, 2 order different.
Great,
Yeah, it
thanks.
seems like it might be difficult to distinguish between the droplet that includes this organic soup that might also include cells versus the cell.
Usually, what I want to also point, and then majority of burst aerosol is dead cell. Because the reason is, think about size of a cell. Cell is several micrometer, even like larger than the 20, 40 micrometer. And then those cells is even like they coming out and immediately go to the water because it's heavy. So when you see the burst aerosol, even they transport to the coastal area, those one is a dead body of a cell, not alive cell. Most of them is dead body. Because the big one, those balls go back to the water. And then something is transportable is a dead body of a cell. And then that brevetoxin is after rupture.
So you can
it sounds
develop...
like it may be the toxin mostly moving with
burst, but like a dead body. Then release from dead body.
Okay, very good. Thank you.
So you could imagine some experiments in your chamber, because you have like this, you know, you're aerosolizing, but you know, you could have this bulk water, and you have wave maker, and you have wind machine, and all.
Yeah, we can. Maybe we can do it, but we need the tank.
Damage the gold chamber.
Tank, and then we have to make a wave.
Oh, you're making waves for sure already. So this is good. Okay, so any other questions from the Zoom room, or I'm going to check back on YouTube. YouTube is pretty quiet out there.
Yeah, may I?
Please, Daniel.
Thank you, Dr. Jang, for this riveting presentation. So you used a nebulizer to actually disperse all of these aerosols. And to my understanding, in the previous work done by like Chang et al. In around 2005, where they did those preliminary models for bloom concentration in the water to the aerosolized brevetoxin content. They also did characterizations of the distribution of the aerodynamic mean of the particulates. So with the nebulization, that'll make very, very small particulates from like the 0.5 to the 1 micron range, which to my understanding is a relatively low fraction of the total sea spray aerosol. And even though those low aerosols are the majority of ones that would penetrate to the lower respiratory system, and what I would assume give the most respiratory irritation, that nebulization seemingly artificially increases the surface area, and then the catalysis for the breakdown of these aerosols. Do you have plans in the future to be doing more like ecologically valid studies on the full range of the sea spray?
That is a good point. Most of nebulizer can reduce particle size. So that's the reason field study is very important. Because if the laboratory investigation should be compared with the field all the time. Otherwise, it's biased. Like for example, I mentioned about the field study, the OM contribution is much higher than chamber. Chamber is OM is less. And then particle size is less. Brevetoxin concentration will be less. Then even I prediction is field OM will be much higher. Brevetoxin concentration is high. When we measure the several time field study, and then that assumption is correct. The laboratory aerosol is different from field. So we need both. Without the data and then laboratory data will be biased.
Right.
But mechanism is still true, like degradation, exposed, those fundamental chemistry is true. So in the future, I have to demonstrate decay of brevetoxin in the field. The bioequation nighttime data and daytime data. Otherwise, just the laboratory data is laboratory.
And in your graph, you showed I think raw or cumulative BTx concentrations. Did you differentiate between the different species of brevetoxins or between backbones A and B?
No, not yet. Yeah, so brevetoxin is a total brevetoxin.
Okay.
This is the ELISA detection, the sensitivity is higher than LC-MS. LC-MS mass analysis require high concentration. It means we have to make sure the demonstration of aerosol sampling technology. We don't want the field. The filter can make lots of bias.
Absolutely.
The test field and the instrument is okay or not. Yeah.
Did you do any pre nebulizing assay for the total content and then post nebulization of the content?
We do some like field aerosol. We have to post nebulize because we need to analyze organic carbon content, right? So we did post nebulization of field sample.
Okay. So I'll jump in because I know that Dr. Jang has a class to teach. She's trying to get off and get to her next class, but it sounds like you guys could have a riveting conversation over the nebulizing issue and many others. So we thank again Dr. Jang for her presentation today, and really excited to see where this research goes. And thanks everyone for attending. We will see you next week.